Okay, the final week of cryptography and data security. Welcome, everyone. Greetings. Okay, this is our final week, and today's lecture is basically pulling everything together. This is kind of basically a big review of everything we covered over the past 6 weeks. Okay, we're not introducing any heavy new math or algorithms. Instead, we're focusing on the core principles of cryptography, how it evolved, how to think like a secured system designer. What are the considerations you have to basically keep in mind when you're talking about securing data? We've covered all of those pieces of information. Uh, Four core principles of modern cryptography: confidentiality. Confidentiality remains, again, only authorized people can read the data. Encryption provides confidentiality by scrambling, so it becomes unreadable, and requiring a secret key to restore it. Examples: encrypted files, secure chat messages, secure web traffic. In other cases, another component is integrity. Integrity means data has not been changed without permission. From the time someone says it to you to the time you get it, or vice versa, nothing has happened to that data or that hasn't been changed. Hash functions and digital signatures protect integrity, detecting even small changes, alerting the system when data is altered. File downloads, software updates, message verification, all of these fall under the integrity category. Authentication, when we talk about this, as far as providing that someone who they claim to be. I'm sending a message to person A. Am I sending it really to person A, or is that someone under a mask who is basically person one? Okay, authentication achieved using passwords, encrypted keys, digital certificates, all the things that we covered over these past 6 weeks. Examples: logging into a system, verifying a service identity, secure network access, and then we have non-repudiation, which means that the sender can't deny having sent the message. We have everything locked down that we know where the message came from and who sent it. Digital signatures provide non-repudiation. Only the sender has the private key. The signature proves the origin and the intent of the message. Digital contracts, signed emails, legal and financial systems. Right, cryptography must be kept evolving. Okay, the main thing is new attacks are discovered. Hackers get better. Okay, and with the hackers getting better, we have to have new technology in order to keep up with the capabilities they have to break the code. This is why some algorithms we discussed earlier are now insecure. They become obsolete because uh, anything that a man creates, it can be worked around. So eventually somebody's going to work around and get a answer and be able to break any kind of code or encryption. So we got to stay ahead as far as what are new things that we can do to reduce that possibility. Post-quantum cryptography. Post-quantum cryptography refers to cryptographic algorithms remain secure if quantum computers become practical. Quantum computers could potentially break some of the current encryption methods, solve certain math problems much faster than classical computers. Okay, all of these things are basically things that are going to make easier for a hacker to get in, but at the same time makes it easier and more, more prudent or more certainty that we can make new cryptographic processes that, because of these new technologies, will make things even harder for a hacker to get into and get to information. What are zero knowledge proofs? Zero knowledge is a cryptographic method that allows someone to prove that they know a secret without revealing the secret itself. Okay, zero knowledge proof. In other words, I can prove I know the password without showing you the password. Okay, It's a new piece of cryptography. Zero knowledge proofs are useful for privacy, preserving authentication, securing identity systems, and reducing data exposure. Zero knowledge proofs. Wave of the future. How cryptography responds to new threats. Cryptography systems evolve, replacing weak algorithms, increasing key sizes, designing new protocols, adapting new software, and attack models. This is why we have MD5, and it's no longer used. Same thing with hash one. Hash one, sash one. Stronger standards replacing old ones. Good security design assumes today's secure may be tomorrow's obsolete. No, not maybe. It will be tomorrow's obsolete. So we have to keep ahead of things. Thinking like a secure system designer, cryptography is not just about algorithms. It's about design choices. What I'm going to choose to make that makes things protected. A secure system uses encryption appropriately, protects keys carefully, combines multiple security keys, avoids unnecessary complexity. Poor design can break even the strongest cryptography. Example, small-scale secure system, perceptual. Scenario, small application allows users to create accounts, send private messages, store files securely. With that, the choices we should kind of embed into that, passwords are hash and salted. Remember, salted is adding an arbitrary number to the key before we hash it. Store files are encrypted. Messages are encrypted in transit. Digital certificates verify server identity. Authentication. Logs protect integrity and hashing. Okay, the system needs to evaluate new design, protect confidentiality, protects integrity, ensures authentication, supports non-repudiation. These are the 4 things that we've basically been talking about over the last 6 weeks. The system's not perfect, but it applies sound cryptographic principles. Okay, this is some repeat what makes the design weak, what makes the design strong. Reuse password, plain text storage, no encryption, common things, the kind of things that you know that you need to avoid for far security. And then the strong design. What are the characteristics of something that has a strong design? And that's basically listed here. As far as the final course summary, over the 7 weeks, you learned that cryptography protects data, identity, and trust. Different tools have different security goals. Strong systems use cryptography correctly and thoughtfully. Cryptography must evolve as threats evolve. You're not expected to be a mathematician, okay? You're expected to be a responsible designer and inform users of cryptographic systems. Cryptography is everywhere, whether we notice it or not. Understand the principle helps you build safer systems. Thank you for your hard work during the term, and be looking forward to your final project presentations. Thank everyone. Hope to see you soon in another one of the courses. Have a good one. Bye.